Welcome back. In this lecture, we're going to be discussing the very basics of a NumPy array, which is our main data structure when working with NumPy and data sets in general. So let's talk about how to create arrays. We'll discuss how to convert existing objects to a NumPy array, such as a normal Python list to a NumPy array. Then, we'll show you some built-in NumPy functions to quickly generate useful arrays. Then we'll talk about creating arrays and matrices of random values. Often in data science and machine learning, we need to quickly create random values in a certain shape, and NumPy has a lot of tools for that. Then, we'll talk about some very basic array attributes, such as data types and shapes. Let's get started. Okay, here I am at my Jupyter notebook. To begin using NumPy, we want to import it. So we will say import NumPy, and then by convention, we import NumPy as NP. Be careful with the spelling of NumPy. Sometimes students get confused with capital N's and capital P's. Everything here should just be lowercase. The stylized convention of capitalizing the N and the P is just for stylizing in the actual naming of the library for things like documentation. But when we import it, we're just going to import NumPy as NP. Let's first discuss how we actually create a NumPy array. So NumPy arrays are essentially the main way we're going to be using NumPy throughout this course. Now, as discussed, we could have a normal Python list, and here I can create one, just my list 1, 2, 3. And if I want to have this or cast it as a NumPy array, I can call the function np array and then pass in my list object. And you'll notice now when it's displayed, it denotes that it's a NumPy array by having array at the front of this. I can also do the same with a nested list. So let's go ahead and say nested list is equal to, and I'm going to create a list of lists. So we'll have 1, 2 as the first object there, then 3, 4, and then 5, 6. So notice here, if I were to ask for my nested list back and just run this, I just get back this list. But if I were to then transform this into a NumPy array, NumPy will actually begin to keep in mind the shape of what's being passed in. And it's going to format this as what is essentially a 2D matrix of 3 rows by 2 columns. And we can see the actual dimensions here by the number of brackets or braces at the beginning and at the end. So this essentially indicates we're dealing with a 2-dimensional object. Now, typically, we're not going to be just transforming normal Python objects to a NumPy array. Instead, there's lots of useful built-in ways to generate arrays. So let's cover a few of those. One way is to use np-arrange, which is similar to NumPy's built-in range function. So we can say np-arrange, it only has one R here. And then what we can do is if you do Shift-Tab, it'll tell you how it works, essentially the same way as Python's built-in range object, where you have a starting point, a stopping point, and then an optional step size. So for example, if we wanted all the integers between 0 and then up to, but not including 10, we can say 0, 10. And that will give us, starting at 10, go all the way up to, but not including 10. So we see the numbers 0 all the way to 9 here. So keep that in mind, this stopping point is up to, but not including it. Then we can also have an optional step size. So by default, the step size is 1. So just go from one integer to the next in a step size of 1. But I can change this to be a step size of 2, which is kind of a quick way to get all the even numbers. So we can say 0, 2, 4, 6, 8. And if for some reason I wanted to continue past this and actually get 10 in there, then I would say go up to, but not including 11, rerun this, and now it includes 10. So we have our starting point, our stopping point, which goes up to, but not including the stop point, and an optional step size parameter. Next, often is the case in data science and machine learning that we want to quickly create arrays of just a bunch of zeros or ones. And to do this, again, NumPy has a built-in convenience function called zeros. And zeros, if you just pass in one number, such as 3, returns a vector of 3 zeros. Something to keep in mind here is you'll notice that it says 0 point, which essentially indicates that these zeros are floating point numbers. And often when you're working with NumPy, and then later on we'll learn about pandas, things are going to be automatically converted to floating point precision numbers instead of being kept as integers. One of the few techniques we're going to be learning about for keeping things in integers is this np-arrange. Pretty much all the other functions we learn about will convert things to floating point numbers. So we have np zeros. If you pass in a single number, it gives you kind of this 1D vector of just those 3 zeros. But you can also say np zeros, and then pass in a shape. So if we do Shift Tab here, notice that it'll say what's the shape you want. So we can say something like, give me a 4x4 matrix, and here we have again 4 rows by 4 columns, all of zeros. Or I can begin to edit this, and we'll see that the second dimension, so if I say 4x10, lines up with the number of columns. So it's how many rows you want by how many columns you want. So here we have 4 rows of 10 columns of all zeros. And if you really want these zeros to be integers, you can begin to edit this data type parameter. So you can say dtype is equal to int if you really wanted these to be integers. For pretty much all our use cases, we won't really have to worry about integers versus floating point numbers. So we'll close that out. So we know NP zeros, and similarly there's NP ones, which is just NP ones, and you can say NP ones 3, which gives you a 1D vector of just a bunch of ones, or you can also pass in a shape, such as 4x4, and there's my 4x4. Notice the sets of double parentheses here. This is essentially indicating that I'm passing in, as my first argument, a parameter of a tuple. And then these outside parentheses are for the actual function call itself. Next, we have linspace, which is a useful function which returns evenly spaced numbers over a specified interval. Not to be confused with what NP-arrange is doing, which is setting a starting point, a stopping point, and then taking some arbitrary step size. NP-linspace instead, the way it works is we say NP linspace, we give it a starting point and a stopping point, but then we ask for the number of actual elements we want evenly spaced between those 2 points. So I can say 3 here, run this, and then it'll return back 0, 5, 10. So these are 3 points, including 0 and 10, including that starting point and the stopping point, and it's 3 points evenly spaced because in between 0 and 5 is 5, and in between 5 and 10, well, that's evenly spaced to also be 5. If we ask for more, so for example, let's go ahead and ask for something like 21 evenly spaced points. We run that, and now we get back 21 elements, going from 0 to 10, where the even spacing is 0.5. So to go from 0.5 to 1 to 1.5, etc. Now, something to note here is that linearly spaced calls actually include that stop value. So to obtain an array of what you may refer to as common fractions, you may need to increase the number of items requested. So often beginners sometimes just go 0 to 10, give me 20 evenly spaced points, and they get these sort of weird fraction calls or weird decimal places. Because we're including the stop value, we may need to do something like increasing the number of items requested to 21 in order to see these common fractions. So just keep that in mind with NP linspace. That's because it's actually including the stopping point this time. Now there's also the capability to create an identity matrix. An identity matrix is simply a matrix of all zeros with a 1 along the diagonal. So for example, if we say np.i of 5, it gives us a square 5x5 matrix with 1s along the diagonal. And this is really useful for a lot of linear algebra tasks. The reason we only need to provide one number is because, by definition, an identity matrix is always square. Okay, so those are a couple of built-in functions in NumPy. Finally, let's show you how to create random arrays. So there's lots of different functionalities with random. And the way we do this is we say np.random. And if you were to hit tab here, you would notice that there's actually a bunch of different random function calls that NumPy has available to us. So many types of random distributions we can call from. So what we're going to do is just show you a couple of very basic ones. There's np.random.rand, and if you ever are confused over what actual random distribution is returned, you can simply do Shift-Tab in the Jupyter Notebook, expand the documentation, and it will report back to you how it's actually grabbing that distribution of random numbers. So in this case, just the call of rand or rand grabs random values from a uniform distribution, meaning everything has the same likelihood of being picked, from 0 to 1. So we'll go ahead and ask for instance, 2 random numbers. And that will give you 2 random numbers with a uniform distribution between 0 and 1. And every time you keep running this cell, notice you'll get back different random numbers, all between 0 and 1. Now, let's say you actually wanted a matrix. So the way this works is you say np_random.rand, and then instead of passing a tuple for this one, what you can do is pass in 2 parameters. Let's say 3 rows by 4 columns. Run that, and now we have 3 rows by 4 columns, all of random numbers between 0 and 1, where all the numbers between 0 and 1 have the same likelihood of being picked. Okay, so that was with a uniform distribution, but there's also the capability to grab it from a standard normal distribution. And for that, we say np random.randn. So randn is doing the same thing from a standard normal distribution. A standard normal distribution essentially just means that the mean is 0 and the variance is 1. So that will actually allow us to then get some negative numbers if we do this. So let's say I wanted 5 by 5, run this, and here we have some negative numbers, and this is a standard normal distribution. It's centered around 0 with a variance of 1. Okay, so we can actually grab random integers by saying np.random.randint, and the way this works is we provide a low and a high, and then optionally we can request a size. Keep in mind the low is inclusive, meaning the low has a chance of being picked, and the high is exclusive, so the high will not have a chance of being picked. So let's go ahead and say we wanted to actually make some random values to try to simulate people's ages. So we could say something like from 1 to 100, go ahead and give me a random number. And this is one way we could then generate random ages. So this person then is 56 years old. And let's say we wanted to quickly generate 10 random ages. The second parameter is just how many we want. So you can ask for 10, and there's our 1D vector. Keep in mind, there's actually a size requested. So we could say something like, give me 2 by 3 as a tuple, run that, and it would kind of structure it out that way, 2 rows by 3 columns. So that is randint. Now you may be wondering, what if I actually want to do some sort of random numbers, but have reproducibility? So every time I run this notebook or run this piece of code, I end up generating the same random numbers. Well, that's where a random seed can come into use. So what I'm going to show you is np.random.seed. And the seed allows you to just pass forth an arbitrary number choice. So the actual number choice isn't that important. The fact that's important is that you choose the same number every time. So let's say I want you to generate the same random numbers on your computer that I'm about to generate on mine. What we can do is choose the same seed value. So I'll choose the seed value of 42, and you can go ahead and type that in. And in the same cell, let's go ahead and say np.random.rand, and then just, let's say I want 4 random numbers. We run this, and if you ran this the exact same way I did with the seed call and the random call in the same cell, then you should see the exact same 4 random numbers. This is going to be really important later on in the course because while we do want some elements of randomness in many of our functions in data science and machine learning, such as a random test train split, we want to make sure, for reproducibility's sake, that your random splits and random values are going to be the same as I show in this notebook. And in order to do that, we'll be using this seed. Now, a question I often get from students is, what's the meaning of this number 42? And it's basically just an arbitrary choice you use to seed what's known as a Mersenne twister, which is a way of generating these kind of pseudo-random values. You can check out the reference link in the notebook for more information on that seed, but in our use cases, basically, we're just going to be using the same seed values as our choice. Now, something to keep in mind is if I grab np.random.rand and then ask for this in another cell, rerun this, I will get now a different set of values than what I did up here. And that's because this is the second call after setting my seed. However, if I keep running these two, they'll always give me the same random values. So often what I would say is try to make sure that your generation of the random numbers is occurring in the same cell as your actual seed value. That way you don't accidentally run this cell multiple times. And you can see here on the 5th one, it's going to give you something different. On the 6th one, it's going to give you something different, etc. So keep that in mind. If you ever want to reset your seed, just go ahead and run that, and then we'll kind of repeat that cycle. Okay, so that's the seed. Finally, I want to show you just a couple of useful array attributes and methods. So often what we can do is we can reshape a 1D vector to any matrix shape we want. So let me go ahead and create an array. We'll do this by saying np_arrange 25. Go ahead and run this. And I'm also going to create an array of random values. So we'll say ran array is equal to np random.rand int. And this will go from 0 to 50. Let's go ahead and just say 10 here. So here's my normal array, which is just the numbers 0 through 24. And my random array are going to be these numbers right here. Keep in mind, depending on how you set your seed right now, you may have different random values than I do, but that's not important for this particular part of the lecture. Okay, so let's say I wanted to reshape this array. When you create a 1D vector, you can ask for dot shape. So let me actually show you that in a new cell. I'm going to say array dot shape, and you'll notice that right now it only has one dimension defined. It just says this is essentially 25 numbers. What I can do is I can reshape this by saying R or ARR reshape, and I can reshape this to be 5 rows by 5 columns. Run that, and now I've taken my original array and reshaped it to be 5 by 5. Something to note is this doesn't actually affect the original object permanently. If I ask for array again, I still get back the original. If I wanted this to be permanent, I could simply just reassign it to array is equal to array.reshape. And here we can see the 5 by 5. Some other things to keep in mind here is that you're not going to be able to reshape the array into a set of dimensions that doesn't make sense. Right now, this is 5 rows by 5 columns, which means I have 25 elements total. If I were to try to reshape that into something like 3 by 6, which would only be able to contain 18 elements, you will get an error. And it will basically say, I cannot reshape something of size 25 into a shape of 3 by 6, because there's only space for 18 elements, and here we have 25. So keep that in mind if you ever see that error with the reshape call. Finally, I want to show you the min, max, and argmax and argmin parameters, or attributes. So we can take our random array, here it is, and let's say I wanted to figure out what the max value of my array was. I'll go ahead and just say off of this, .max, open and close parentheses, and it'll return back the max value in the array, which happens to be 43 in my case. Now let's say I was actually interested in the location, or index location of that max value. The way that works is I say arg max, run that, and that will give me back the index location. So the index, just like a normal Python list, starting at 0, so 0, 1, 2, 3, 4, 5, 6, 7, and there's the max value of 43. Similarly, we can do the same with min, so I can ask for the minimum value, which is 1, and I can also ask for the minimum value location, which in this case is occurring at index 5. And finally, there is the data type attribute. You can also grab the data type in the array. So I can say something like ran r dtype, run that, and it'll report back this is a 32-bit integer. Or if I were to check some of my other ones, for instance, let's go ahead and set this. I'm just going to copy and paste this random array here. So my array, run that. We can see here that these look to be some sort of floating point. I can always check that by saying, what's my data type, or dtype. Notice I don't have open and close parentheses here because that's actually an attribute. And it will tell me that these are 64 floating bit numbers. Okay, that's the very basics of NumPy arrays, generating NumPy arrays, both built-in functions and random values, as well as things like shape, reshape, and data type. Thanks, and we'll see you at the next lecture.